Hi, welcome back. This is the first of three lectures about OpenACC. In this lecture, we have two main points. The first point is about what is OpenACC. OpenACC is a compiler technology and consists of a set of compiler directives, library routines, and environment variables for programming GPUs. The second point is that we are going to implement our first program in OpenACC by simply annotating serial C code with a series of pragmas or compiler directives. OpenACC is a compiler technology. That means that we need a compiler that supports OpenACC. We're going to annotate our C code with the so-called pragmas or compiler directives. The compiler will catch the compiler directives and translate them to some code for GPU. The OpenACC framework consists of a number of compiler directives, library functions, and environment variables. OpenACC supports codes written in C and Fortran and supports also C++. But to use OpenACC in C++ code is a little bit more cumbersome. The specs defining the OpenACC pragmas were originally developed by the Portland Group Inc., that is the PGI company. The PGI company is being bought by NVIDIA in 2013. For this reason, the PGI implementation of OpenACC standard is done in CUDA. Approximately around 2010, compiler vendors started to look at directives for GPU to simplify the way to program GPUs using compiler. At its inception, OpenACC intended to be for all different kinds of accelerators. However, it ended up in supporting only NVIDIA GPUs. OpenMP, that is an approach similar to OpenACC, has the goal of supporting all different kinds of accelerator. The OpenACC standard was released in November 2011 at the Supercomputing Conference. The standard is mainly supported by Cray and PGI. In the future, OpenACC will be replaced by OpenMP. The OpenMP4 standard has support for accelerator. However, currently few compilers implement support for OpenMP4. The good news is that if you know OpenACC, it will be very easy later on to use OpenMP. One big difference between OpenACC and CUDA is the use of compiler directives in OpenACC. To understand what a compiler directive is and the advantage of using compiler directives, let's take a look at our first OpenACC program in these slides. The code does the matrix multiplication. The code in these slides is almost identical to the sequential version, except for the two lines with the pragma. In C, the pound pragma directive is the method to provide to the compiler information that is not specified in the standard language. OpenACC uses the compiler directive mechanism to extend the base C language. In this example, the pound pragma tells the compiler to generate code for the I loop block so that the loop iterations are executed in parallel on the accelerator. The copy in clause and the copy out clause specify how the matrix data should be transferred between the host and the accelerator memories. In particular, we are telling the compiler to memcopy the arrays am and n, and memcopy back p to the host at the end of the parallel region. This pound pragma ACC loop instructs the compiler to map the inner J loop to the second level of parallelism on the accelerator. Remember that we are already in the parallel region on the GPU because we are in the I loop block. So this is a nested parallelism. Not all the compilers support OpenACC. The PGI compiler supports OpenACC and we are going to use it for our assignment. If you are using PGI compiler on your laptop, on your workstation, you need to call the C PGI compiler called PGCC. On the supercomputers, remember to swap the compilation environment from the default one to the PGI compiler framework. Then you will call the C wrapper to call the PGI compiler. The most important thing is don't forget about the -ACC flag. If you don't provide this flag, the pragmas will be ignored and we will only run the code as a serial code. So what are the advantages and disadvantages for OpenACC? Well, the first advantage is that we don't need to completely rewrite the code if we have an existing code that we want to port it to GPU. Some existing scientific applications are large, and their developers don't want to rewrite them for an accelerator. OpenACC lets these developers keep their application looking like normal C or Fortran code, and they can go in and put the directives in the code where they are needed, one place at a time. Second, by using the compiler directive approach, OpenACC allows a programmer to write OpenACC program in such a way that when directives are ignored, the program can still run sequentially and gives exactly the same result as when the program is run in parallel. A disadvantage of OpenACC might be the performance when compared to the performance of pure CUDA code. Therefore, the performance of an OpenACC program depends more on the capability of the compiler itself and its support for OpenACC. In summary, in this lecture, we look first at what OpenACC is. We then added pragmas or compiler directives to offload loop of computation to the GPU. In the next lecture, we're going to look at more in detail how to use the parallel and loop constructs to offload computation to GPU using OpenACC. We're done with this lecture and talk to you soon.